WebAssembly is no longer confined to the browser. Through the WebAssembly System Interface, or WASI, it has migrated outward into back-end infrastructure. It now runs serverless functions, powers IoT devices, and drives global edge networks. By design, WebAssembly secures these environments by isolating memory through software fault isolation and restricting arbitrary jumps using control flow integrity policies. But its highly optimized deterministic compilation process produces identical binaries. When deployed at scale, this creates a vast monoculture where millions of edge nodes execute the exact same bytecode. If a speculative execution vulnerability, like Spectre, is found in that bytecode, it exists identically across every single node on the network. Attackers only need to map the timing and memory layout of one local binary to develop a write-once, exploit-everywhere payload. In massive decentralized environments, strict determinism ceases to be a feature of stability. It becomes a severe architectural liability. To secure these decentralized execution environments, we must implement automated software diversification. The goal is to generate program variants that are structurally and behaviorally unique, yet mathematically and functionally equivalent. This controlled unpredictability destroys the reliable baselines that attackers require to execute memory and side-channel exploits. To achieve this at scale, diversity is injected at two specific points in the deployment pipeline. The first point is during compilation, directly modifying the LLVM intermediate representation. The second point is post-compilation, rewriting the final compiled WebAssembly bytecode itself. Shifting security from the hardware layer directly into the compiler pipeline enables a proactive moving target defense at the edge. In standard pipelines, source code moves through a front end, translates into an intermediate representation within the transformer block, and passes through a back end into a WebAssembly binary. This LLVM intermediate representation provides an optimal stage for injecting diversity before the code is finalized. Crow is an automated tool engineered to intercept this LLVM intermediate representation and apply enumerative synthesis. The algorithm first scans the intermediate representation to isolate and extract instructions that return integers. It then builds a data flow graph for these isolated instructions, systematically generating every possible alternative mathematical expression that could replace them. To ensure the program operates correctly, an SMT theorem solver verifies that every new mutant expression produces the exact same output as the original. Because Crow deliberately disables standard compiler pruning strategies, it can perform radical structural transformations, a process known as constant inferring. In a scenario like the Babbage problem, which uses a loop to search for a specific mathematical condition, Crow can force massive loop unrolling to calculate the branching logic prior to runtime, collapsing the entire search into a single constant assignment. The resulting variant maintains the exact same output, but it operates with a completely different control flow and memory footprint than the original source code. Compiler-level synthesis achieves deep structural mutation, but it requires access to the source code. This necessitates a secondary approach for pre-compiled binaries. Once these variants are generated, they must be physically deployed to the end user or edge node. This deployment is managed by MIWI, an architecture designed for multivariant execution for WebAssembly. MIWI compiles hundreds of the variants generated by Crow and packages them together into a single, massive multivariant WebAssembly binary. During runtime, every incoming function call is randomly routed to a completely different internal variant. When deployed on modern edge computing platforms, this creates an active moving target defense. Attackers attempting to profile short-lived serverless functions are constantly fed different execution traces, preventing them from establishing the baseline required for an exploit. MIWI bridges the gap between theoretical diversity and active defense by randomizing the execution path on every single invocation. Security engineers frequently inherit third-party compiled WebAssembly binaries where the original source code is entirely unavailable. Wasm Mutate is a compiler-agnostic tool built to operate directly on the raw bytecode of those precompiled binaries. Modifying WebAssembly binaries means navigating rigid constraints. Sections require a precise structure, a 1-byte ID, an 8-byte size, and a measured content block. Inside, break instructions are tethered to specific enclosing block depths. If altered, every nested break instruction must be mathematically recalculated. To navigate these strict constraints, Wasm Mutate uses a data structure called egraphs, or equivalence graphs. These egraphs map out overlapping, functionally equivalent instruction sequences directly onto the existing bytecode. As Wasm Mutate swaps these instruction sequences, it algorithmically recalculates all block depths and section sizes to ensure the binary remains valid. It also inserts dummy blocks and no operation padding, radically altering the binary's static signature. This process operates with extreme efficiency, generating tens of thousands of valid, unique variants in a matter of minutes. eGraph traversal proves that precompiled bytecode is not rigid. Post-deployment systems can actively rewrite their own instruction sets to protect themselves. Breaking the WebAssembly monoculture produces direct, measurable defensive outcomes. The primary use case is mitigating hardware-level side channels and speculative execution vulnerabilities. This timeline measures sequential cache reads. To execute a side channel attack, an adversary relies on this predictability to measure exact timing deltas on the processor cache. Randomized execution paths continuously fracture the CPU's timing sequence, transforming those predictable cache reads into unreadable noise. Furthermore, randomizing the memory layouts destroys the spatial predictability an attacker relies on to target specific cache lines. Defensive diversification effectively starves side-channel exploits of the deterministic environment they require to function. Security researchers also use this technology offensively for red teaming and malware generation. By feeding known cryptojacking malware into Wasm Mutate, researchers can spawn thousands of uniquely structured variants. The immediate objective is to break traditional, static antivirus signature checks by shifting the binary's hexadecimal signature while maintaining its malicious payload. The ultimate goal is to expose the brittleness of hash checks and force the cybersecurity industry to adopt dynamic behavioral analysis models. In globally distributed infrastructure, predictable execution is a critical vulnerability. Security in the WebAssembly era requires abandoning static permanence, engineering structural unpredictability into the code itself.